Magnetic resonance imaging, also known or better known as MRIs, is a technique for creating detailed images of the human body. A lot of doctors like to use this method because it's non-invasive and painless, and there's no ionizing radiation, which could cause harm in the future, like X-rays or CT scans if used a lot. And this relies on the simple equation. The magnetic field is equal to the vacuum permeability multiplied by the number of turns in the coil multiplied by the current in the coil, all divided by the length of the coil. Or, as we know it better, the magnetic strength of the field is equal to the flux density, or the flux over area. And just as the equation, and we know it, magnetic flux is equal to the magnetic field strength multiplied by the cross-sectional area. The human body is mostly water, about 72%. Water molecules, H2O, contain hydrogen nuclei, just a single proton, which becomes aligned in a magnetic field, like so, in the north upwards position or the south upwards position. An MRI scanner applies a very strong magnetic field, about 1/5 to 3 Tesla, or roughly 1,000 times the strength of a typical fridge magnet. Most often it's about 1.7, which aligns the proton spin in this manner. The scanner also produces a radio frequency that creates a varying magnetic field, in addition to the first magnetic field that aligns the proton spins. When this radiomagnetic field is applied, the protons absorb the energy from this field and flip their spins, like so, and vice versa for some of the others. But it's not all of the protons, but this is the basic picture. When the field is turned off, the protons gradually return to their normal spin, a process called precession. This is the change in orientation of the axis about which the proton is rotating. So as the proton is rotating in a counterclockwise direction around the vertical axis, precession means that this axis is changing from north downwards to north upwards. The return process produces a radio signal that can be measured by receivers in the scanner and made into an image. And it's based on this underlying principle. The angular precessional frequency of the proton is equal to a gyromagnetic ratio, a constant, multiplied by the strength of the external magnetic field, the variable radio frequency that was applied. Protons in different body tissues retain their normal spins at different rates, so the scanner can distinguish among tissues by how fast the protons return to their normal spin. The scanner settings can be adjusted to produce contrast between different body tissues, such as in this image, to get detailed images of the brain or other body parts. Additional magnetic fields are sometimes used to localize body structures in 3 dimensions.